we're going to look at some special relationships in mathematics that are represented by straight lines on a graph. And these relationships are called linear relationships or linear functions. In order for us to best understand these linear relationships, it's nice if we can talk about a story that would represent a situation like this. So let's think about the situation of a walkathon. So in our story, we have a class that's decided to participate in this charity event. So each participant is going to find sponsors or people who are going to donate a certain amount of money for each kilometer that each student walks. So they've decided to make this a friendly competition. And one of the students, Leanne, suggests that they determine their walking rates in meters per second. So maybe they can make predictions about who's the fastest walker or who might raise more money in a given amount of time. So that walking rate is going to tell us how fast a person can walk in a particular amount of time. Most of the time when we're talking about rates like this, we use a unit rate, which is one of those situations where we have a denominator of 1. We use these all the time in day-to-day life. For example, when we get in a car and we travel down the highway, we can talk about how fast we're traveling. We might be traveling at 50 miles per hour. And from that, we can determine how far we would travel in different amounts of time. So if you know I'm traveling at 50 miles per hour, you can predict that in 2 hours I would travel 50 times 2 or 100 miles. You might also see this when you're shopping. So for example, if you're going to purchase milk, it's nice to know how much 1 gallon of milk costs. So if we're looking at a rate of $3 per gallon, that is a unit rate. When your parents drive into the gas station to fill up their gas tanks, the sign at the outside talks about the unit rate of how much it costs per gallon of gas. So they have to use that to calculate their total cost based on how much they purchase. So back to our story. In this particular class, we have 3 students who've given us their data. Elena knows that she can walk at 1 meter per second. Gilberto knows he can walk at 2 meters per second. And Leanne knows that she can walk at 2.5 meters per second. So like I was mentioning, from this one piece of information, we can set up a table of data about each walker. So let's start with Elena. At the beginning of the race, before the time for the walkathon even starts, we know that no time has passed, so we know that Elena has walked 0 meters for the walkathon. But based on her unit rate, her meters per second, we know that once the race starts, after 1 second, she's going to travel 1 meter. And from that, we can determine that in 2 seconds, that's double the amount of time we were talking about, she's going to walk 2 meters. In 3 seconds, we know that she's going to walk 3 meters. In 4 seconds, we know 4. Now, using this pattern and the information that you know, go ahead and complete this table for Elena's walking rate. And remember to think about time and the amount of the distance that she's walking in that particular time. Don't just go down the columns, go row by row. And after you've completed Elena's graph, stop the video and complete the tables for Gilberto and Leanne. Think about their unit rate. Always start with 0. At 0 time, Gilberto's walked 0 meters, but in 1 second, we know he can walk 2 meters. So think about how far he'll walk in 2 meters and in 3 meters, or sorry, in 2 seconds and 3 seconds, and so on. Do the same for Leanne. Watch your calculations, look carefully. Once you've filled out all the tables, restart the video and check your work against the next slide. Okay, here's the information we have. Double check your calculations. Notice that in all 3 tables, we kept the time at a consistent interval. We went 0, 1, 2, 3, 4, 5, all the way through 10. But the distance that each person has walked is different from person to person. So we've taken that one piece of information, that unit rate, and we've created a table of data. So as mathematicians, sometimes it's nice to see the picture of that data. So this is that time that we can take a table and we can go to the coordinate plane and make a graph. So we're going to start with Elena's information. And Think about science for a minute, and I know you've all graphed information in science. Well, graphing in mathematics is very similar. Our independent variable is always on the x-axis, right down here. And we would also refer to this as mathematicians as our input. So please take a moment, label that x-axis, it's time in seconds, mark that it's the IV, the independent variable. It's our x coordinate, and it's referred to as our input. Oh, back on our table, that same information is in the first column for us. So mark that same thing. This is our information for our IV. It will go on our x-axis and is the input for all of our coordinate pairs. Our DV, our dependent variable, the distance a person walks, depends upon the time that's passed, is on the y-axis. So mark that carefully. On the y-axis, this is the DV. Mathematicians might also call that the output. And the DV is going to occur in our table in the right column. So our DV is here. It goes on our y-axis, and again, it is the output of our data set. So we can take Elena's data and we can treat each row like a coordinate pair. We know that at 0 seconds, she's walking 0 meters. At 1 second, she's going to walk 1 meter. At 2 seconds, 2 meters. And we can go all the way down the table creating this graph from the data. Now once you've plotted the points, you'll notice that if you connect the dots with a ruler and a straight edge, you get this line going up your graph, and that's what we're looking for. And this is why we can call this a linear relationship, because Elena's data would create this line on the graph. Notice on our graph, we have labeled the x-axis with our IV, we've labeled the y-axis with our DV, and notice we've also got a good title on that graph, and we can title these graphs just like we do in science, the effect of the IV on the DV. So make sure that your graph has all of this information, and then it's time for you to graph the other two students' data. So grab a different color marker or color pencil and plot their data on the graph. Now you'll notice that Gilberto's distances go past 10, and 10 is the maximum number on your graph, and that's okay. Plot all the points you can, using them as coordinate pairs, and then connect the dots and create that line. On Leanne's data, look at the points carefully. You won't be able to plot them all, but you've got 3 good points that you could use to create her line as well. So plot those points, use a straight edge to connect the lines in different colors, and then restart the video when you're done to check your work. Alright, so here's what our graph should look like. Notice I've got 3 different colors. You can still see Elena's walking rate represented by the red line, Gilberto's is represented by the purple, and Leanne's is in green. You'll also want to remember to include a key on your graph so that you know what color is representing each student in this story. The last thing I'm going to ask you to do is to write an equation that shows the relationship between the time that passes in the race and the distance that each student walks. So let's take a look at the table, and I like using Gilberto's for this example. We don't see much on the 0 timeline, but if we go down to 1 second, I notice that I can take the number of seconds that pass and I can multiply it by 2 to get the distance in meters. And I notice that if I take 2 seconds and multiply that by 2, which happens to be Gilberto's walking rate, I get his distance walked. The same thing with 3. If I take the time and multiply it by Gilberto's walking rate, I get his distance, and it still works out with 4. And if you'll check out the rest of the table, you'll notice that as well. So that in order to write the equation for Gilberto's walking rate, I'm simply going, or his distance walked, I'm sorry, I can simply take his walking rate, multiply it by the time he's walked, and I will get that distance. All right, one more time. It is your turn. You are going to stop and write equations for these students representing their distance walked using their rate and time. Once you've written these equations, restart the video, check your work to see what you've got. All right, let's take a look at Elena's first. Her walking rate is 1 meter per second, and if we multiply that by t for time using the IV, we're going to get her distance walked, and that's the dv. Now sometimes, because Elena's walking rate is just 1, mathematicians don't always write that in front of a variable, so you might see this equation written as time equals distance. But Gilberto's equation doesn't work like that. He has a walking rate of 2 meters per second. So we would multiply 2 times t, or times the time every time, to get his distance. And Leanne's is 2.5 times the number of seconds walked. So 2.5 t equals d. And notice that all three of those equations represent the rate times the independent variable equals the dependent variable. But you can turn that whole statement around and say the dv equals the rate times the IV. And this is the big idea to wind this lesson up. Make sure you understand that to find the dependent variable, the outcome on all of these stories, we took the rate and multiplied it by the time, or the IV. As you finish this lesson, please be sure that you can create a table for a story based on a rate of change. Make sure that you can take that information and graph the linear function from the table, and that you can identify the independent variable and the dependent variable in a table, on a graph, and an equation.